This video is all about convex and concave functions and non-stationary points of inflection. Now, some of the words there will be familiar to you from year 12 and some of them won't be. So the first thing I want to do is go back to year 12 and have a quick recap on some terminology, and then we'll show how that then comes into these words. So, in year 12, if we had a function y equals f of x, we would say that that function is increasing if the gradient is positive, because it would be going up. We would say the function is decreasing if the gradient was negative, because the function would be going down at those values. And we said that there's a stationary point where the gradient is equal to 0. So that might look like a curve where you have a maximum, or you might have a curve where you have a minimum, or you might have a curve where you have a point of inflection there. Now we could determine which one of those it was by taking the second derivative. So when you found the second derivative and you substituted the x value in, if you got a positive number, then that told you that you had a minimum. The curve, the stationary point was here, and you had a minimum like this. If you had a negative, so if the second derivative was negative, then that told you you had a maximum. So the curve would look like that. Or, finally, if the second derivative was equal to 0, we needed to do some further investigation, because we weren't sure whether it was going to be a minimum or a maximum. Or it could have been this point of inflection. So what we had to do was, let's say that we found that a stationary point was at x equals 5. We checked the function before that, we checked the gradient before that, so we worked out what dy by dx was when x is, let's say 4.9, just below that, and we were checking to see, is it an increasing function or a decreasing function before 5? And then we found dy by dx just after 5, so let's say when x was 5.1. And again, we were checking to see whether it was an increasing function or a decreasing function. So the idea was that if we found that it was increasing here and decreasing here, so increasing and then decreasing, that told us that it was a maximum. Or if we found that it was decreasing here, so negative here, but increasing here, so positive there, then it would be decreasing, then increasing. So we'd found that it's a minimum. Or finally, if we found that the gradient was positive here and positive here, then we knew it would be increasing, then increasing. So we had a point of inflection. Or finally, we found that if it was negative here and negative here, again, we had a point of inflection like that. So that's recapping everything that we saw in year 12 when we were looking at finding stationary points and their nature. Now, the second derivative doesn't just apply at stationary points. The second derivative, all that means is the rate of change of the rate of change. So you'll remember that I wrote it like this when I did the video on the second derivative in year 12, because it's the rate of change of the rate of change. And it doesn't have to be only applicable to the stationary points. At any point on the curve, you will have, you can find the second derivative. And the idea of this convex and concave function relies on the second derivative. So we define a function as concave if the second derivative is negative. And so that would look like any part of the graph where you have a curve looking like that. So if the curves go down like that, or even up like that, then we'd say that it's that part of the function is concave. Because it's kind of similar to the idea of year 12, where when we found the second derivative was negative, that told us there was a maximum. You can see these are kind of like having a maximum. But the whole function is going to be, the function is concave if the second derivative at each one of these points is negative. A function is convex where the second derivative is positive. So that would be where the curve looks like that, or could be like that as well. Again, it's similar to a minimum. The difference is when we talk about a maximum or a minimum, we're talking about at a specific point, at the turning point. Here I'm talking about how the whole curve is behaving for a range of different values of x. Not one specific value of x, but a whole different range of x's. So at each point along this curve here, the second derivative would be positive. At each point along this curve here, the second derivative would be negative. So we say that this part, the function is concave here, and we say the function is convex here. Where a function changes from being concave to being convex, or vice versa, that is what we call a point of inflection. So a point of inflection is where the curve changes from being convex to concave. Or vice versa. It could be the other way around. So, in the context of the stationary points of inflection that we saw in year 12, if I have a stationary point like this, we can see that the curve is concave here, it is convex here, and the point where it changes is my point of inflection. It changes from being convex to, changes from being concave to being convex. Or, if I had a curve like this, then my function is changing from being convex to concave. So I have a point of inflection there. So those are the two types of points of inflection that we saw in year 12, the two stationary points of point of inflection. So at this point here, the curve does change from being concave to convex, but also the gradient was 0. That's what we saw in year 12. And the same thing I did there. However, you'll have noticed on my first slide here, I said about non-stationary points of inflection. Because a point of inflection doesn't actually have to be a stationary point. For example, if I drew a curve like this, quite difficult to see here, but it's changing from being concave to being convex, and there's not actually a stationary point in between. There's no point here where the gradient is actually 0. The gradient at each point on this curve is non-zero. There is no stationary points on this curve that I've drawn here. But there is a point of inflection there. So you can have non-stationary points of inflection where the gradient is not 0, but the graph does change from being convex to concave, or vice versa. So let's have a look at an example. We'll do two examples. First one, you're given that y equals x cubed minus 6x squared plus 15x minus 10. We need to find the coordinates at which the second derivative is 0, and we need to show that that is a point of inflection. So, first thing, let's find the first derivative. So dy by dx is going to be 3x squared minus 12x plus 15. So that's differentiating for the first time. Then differentiate for the second time. We get 6x minus 12. And I need to find the coordinates of the point at which the second derivative is 0. So when does that equal 0? Well, hopefully we can see that's going to be when x equals 2. And when x is 2, y equals, if I substitute 2 up in here now, so I'll get 2 cubed minus 6 times 2 squared, so 6 times 4, plus 30 minus 10. So what's that? 20 minus 4, so that's 4, I think. Okay, so we've got the coordinates where the second derivative is 0, but I also need to show that that is a point of inflection. So I've done the first part, I've found the coordinates where the second derivative is 0. I now need to show that that's a point of inflection. The point 2, 4 is a point of inflection. Well, remember, a point of inflection is where the graph changes from being convex to concave, or vice versa. So I need to show that. I need to show that when x is 2, the graph changes from being convex to concave. So, let's consider just before 2. So let's say when x equals 1.9, how does the curve behave when x equals 1.9? So I can substitute that in to my second derivative. So d2y by dx squared and if I substitute 1.9 into here, hopefully you can see we're going to get negative. 6 times 1.9 minus 12, it's going to be negative. Check that on the calculator for yourself if you want to. So I can see that when x equals 1.9, just before 2, the function is going to be concave because the second derivative is negative. When x equals 2.1, if I substituted 2.1 into my second derivative, I get a positive number. 6 times 2.1 minus 12 is positive. Therefore, the second derivative is positive and it would be convex. So at the point x equals 2, the function is changing from being concave to being convex, and it is a point of inflection. So I have shown that that is a point of inflection with this working out. And now I could write a sentence and say that. Part 2. Find the gradient of the curve at the point of inflection. So, the point of inflection was when x equals 2. So if I substitute that into the gradient function, if I take that and substitute that into here, so I'll get dy by dx equals 3 times 2 squared minus 12 times 2 plus 15. And I think that gives 3. Yeah, I think that gives 3. So the gradient of the curve at the point of inflection is 3. So it's not a stationary point. It's a non-stationary point of inflection. So at that point, there's no stationary point, but the graph does change from being convex to being concave. Part 3. I need to show that there is no turning points. So I know that a turning point is where the second derivative is equal to 0. So the first derivative was this. Okay, so if there was a turning point, dy by dx would equal 0. And if I want to show that there's no turning points, if I just consider the discriminant of this equation, if I do b squared minus 4ac, and I'll just try and show that this is going to be negative, because if the discriminant is negative, there are no solutions to this equation, therefore there can be no turning points. So if we do that, we'll get minus 12 squared minus 4 times 3 times 15 which is 144 minus 15 times 12 is going to be 4 times 180, which is minus 36. So that's negative, so I can now write a sentence and say the discriminant is negative, therefore there are no roots to this equation, therefore there are no turning points. And finally, penultimately, part 4 finds the coordinates of the point where the curve crosses the x-axis. So I know it's going to cross the x-axis when y equals 0. So let's go back to the original curve, which was this. So when does that equal 0? Now to solve this equation, you could use the factor theorem, or you've got your your graphical calculators, so you could just use your calculator to solve this cubic equation. And I think you find that there's only one root of this equation. I think it's 1. I think if you type that into your calculator, solve that equation, I think you get x equals 1. Or like I say, you can use some year 12 knowledge and use the factor theorem to solve that. So anyway, part 5 now, to sketch the curve. And obviously you've got your calculator to help you with this as well. But the key things we've found so far. We know it crosses the x-axis when x equals 1. It's going to cross the y-axis when x equals 0. So when y equals minus 10, I'll put a 0 here, here, and here, I get y is minus 10. I know that there are no turning points, because there's no stationary points at all, and I know there was a point of inflection when x equals 2 and y equals 4. We had that from before. Yeah, 0.24 was a point of inflection. So the point when x equals 2, y equals 4, roughly there. That was a point of inflection. I know that the function was concave to the left of that, and it was convex to the right of that. So it will look something like this. Like that. So it's concave. Here's my point of inflection, so it changes to be convex at that point. That point there was not a stationary point. The gradient of the tangent at that point, if I were to draw a tangent at that point, the gradient of the line there would be 3. We worked that out before. But obviously I wouldn't put that onto my sketch. There we go. So hopefully that example shows what a concave function looks like, how we can find it. Remember the second derivative was negative there when x was 1.9 or smaller than 1.9. The second derivative was negative there. It was convex when the second derivative was positive. Where there's a change between concave and convex, there is a point of inflection. The second example I'm going to do, I've already put a load of working out here, so I'm not going to go through in a huge amount of detail. I'll just talk over it, basically. It says you are given that y equals x to the power 4 minus 2x cubed. Find the coordinates of the stationary points of the curve and determine their nature. So, as usual, stationary points we would differentiate, I've done that here, make it equal to 0, solve that equation, so I've done that here, and I found that x equals 0 or x equals 3 over 2. I then took both of those numbers and substituted them back in there to get the y coordinates. So I found that there was 2 stationary points, one at 0, 0, the other one was at 3 over 2 and minus 27 over 16. Then I wanted to determine their nature. So I found the second derivative and I substituted the x coordinates in. So I substituted 3 over 2 in and I found that I got a positive number. When I substituted 3 over 2 into here, I got 9, which is positive. Therefore, that told me that that point was a minimum. So I figured out that the coordinates 3 over 2 minus 27 over 16 was a minimum point. So all of this so far is all the same as GCSE. Sorry, as year 12, not GCSE. Then I did the same thing with the other stationary point when x was 0. So I substituted 0 into the second derivative, and I found that the second derivative was 0. So then what I would have to do is to consider either side of that point. So I've considered when x equals minus 0.1 and when x equals 0.1, and I'm going to consider, is the function, either side of this, is the function concave or convex? So if I substitute the minus 0.1 into d2y by dx squared, if I substitute minus 0.1 into the second derivative, I find that I get a positive number. And similarly, when I substitute plus 0.1 in, I found that the second derivative was negative. So I found that on one side of 0, the function was convex, and on the other side of 0, the function was concave. There had been a change from being convex to concave, therefore, the coordinate 0, 0 was a point of inflection. And it was a stationary point of inflection as well, because the gradient was 0 at that point. The second part of this question says, find the coordinates of the point at which the second derivative is 0 and show that that's a point of inflection. So, I took my second derivative that I already found out, made that equal to 0. I solved that equation, so if I factorise that out, I get this. So I find that x equals 0 or x equals 1. Now, the x equals 0, well, we've already kind of talked about that one already. We already know the coordinate 0, 0 was a point of inflection. We've already figured that out. But we've got this second coordinate now, when x equals 1. If I substitute 1 into the original equation, I get that y is minus 1. And I now just want to show that this is going to be a point of inflection. So if I consider either side of 1, so over here I've said x is 0.9. I've substituted 0.9 into the second derivative, and I found that it's negative. Then I considered the other side of 1, so when x equals 1.1, I found that the second derivative was 33 over 25, so positive now. So again, the function has changed from being concave to being convex, so there is a point of inflection at the coordinate 1, minus 1. So far in this question, we've found out that there's two stationary points, 0, 0, and 3 over 2 minus 27 over 16. One of those was a minimum, and one of those was a point of inflection. Then in part 2, we found out that there was also another point of inflection that was not a stationary point, so a non-stationary point of inflection. The coordinate's 1, minus 1. To sketch that, and again, you can put the equation into your calculator and you'll get a graph like this. Like I say, we've got the point of inflection at 0, 0. We knew that the function was convex before that and concave after that. Then there was another non-stationary point of inflection at 1, minus 1. You can see the function is concave here, but then changes to be convex here, either side of that point of inflection. And then we had the usual minimum over here as well. So there we go. So from this video, I want you to understand what a convex function and a concave function look like, and how you can find them using the second derivative, and how they relate to, or also don't relate to, stationary points. You can have a stationary point of inflection, but you can also have a non-stationary point of inflection as well. The point of inflection just refers to the changing from being convex to concave, or concave to convex. It doesn't necessarily have anything to do with whether the gradient is 0 or not 0 at that point.